curious minds. Welcome back to Projexcellence Prodigy, your one-stop destination for understanding project management and mechanical engineering concepts in a simple and practical way. I'm Govind, a PMP certified professional and a mechanical engineering graduate with more than 25 years of experience in power plants and the utilities sector. In our Evergreen Mechanical series, today we are going to discuss the difference between heat engines and heat pumps. You may have heard these terms. Both systems deal with heat and energy transfer, but they work in completely opposite ways. One system converts heat into useful mechanical work, while the other uses mechanical work to move heat from a colder region to a hotter region. In this lesson, we will clearly understand what a heat engine is, what a heat pump is, how their working principles differ, and the key performance parameters like thermal efficiency and coefficient of performance COP. So let's get started. A heat engine is a device that takes heat energy from a high temperature source, converts part of that heat into useful mechanical work, and then rejects the remaining heat to a low temperature sink. Heat engines are IC engines, either petrol, diesel, or gas engines, steam turbines, and gas turbines. The function of the heat engine is very simple. Consider a car engine. Fuel burns inside the combustion chamber and produces hot gases, and these hot gases act like the hot reservoir. Engine absorbs heat Q1 from this hot reservoir and converts part of this heat into piston motion, which produces mechanical work W. And the remaining heat Q2 is lost through exhaust gases, lube oil, cooling system, and surroundings, which act like the cold reservoir. Now recall the first law of thermodynamics from our last lesson. It says energy can neither be created nor destroyed. It can only be converted from one form to another. So, energy input in a system will be equal to energy output. So, in that case, heat supplied to the engine will be equal to work produced W plus heat rejected Q2. The heat entering the engine is divided into two parts. One part becomes useful work and the other part becomes waste heat. Here comes a very important concept. A heat engine can never convert 100% of heat into work. That means Q2 can never be zero. There must always be some heat rejected. This is what the second law of thermodynamics states, that heat cannot be completely converted into work in a cyclic process. Some heat must always flow to a lower temperature sink. That is why the cold reservoir is essential for the operation of heat engine. If you see this equation here, W is equal to Q1 minus Q2, the larger the temperature difference between hot and cold reservoir, the greater the potential to produce useful work. Now let's talk about thermal efficiency. The thermal efficiency of a heat engine is defined as eta equals W by Q1. This tells us what fraction of the input heat is converted into useful work. Let us understand this with a simple example. Suppose the engine receives 1000 joules of heat. So Q1 equals 1000 joules. Out of this, 600 joules of heat is rejected. So Q2 equals 600 joules. The work output will be 1000 minus 600, which equals 400 joules. So the efficiency becomes 400 divided by 1000, which equals 0.4 or 40%. So 40% of the heat becomes useful work, while 60% is rejected as waste heat. Thermal efficiency of heat engines is always less than 100%. There are several reasons that limit the efficiency of heat engines. The first and most important reason comes from the second law of thermodynamics. According to the Kelvin-Planck statement, it is impossible to build a heat engine that converts all the heat supplied into work without rejecting some heat to a lower temperature sink. This means a heat engine must always reject some heat to a cold reservoir. And in real engines, heat is continuously lost through cylinder walls, cooling systems, exhaust gases, lube oil, and radiation. So this lost heat cannot be converted into useful work. We also have combustion losses. In internal combustion engines, fuel does not always burn perfectly. Sometimes there is incomplete combustion, which produces unburnt fuel or carbon monoxide. This means part of the fuel energy is always wasted. Because of all this, 100% efficiency is impossible. The second reason can be understood from the efficiency equation. The maximum theoretical efficiency of heat engine is 1 minus Tc divided by Th. Th is the temperature of the hot reservoir and Tc is the temperature of the cold reservoir. In this equation, efficiency can be 1 or 100% only in the case if this Tc by Ts fraction is least or 0. For this, either denominator value should be very high or numerator value should be very low. For denominator, limitation is the temperature of the heat reservoir cannot be extremely high because engine materials have temperature limits. At very high temperatures, components may fail due to melting, oxidation, or creep. For example, modern gas turbines typically operate around 1400 to 1700 degrees Celsius, which is already close to material limits. And for numerator, the temperature of the cold reservoir can never reach absolute zero because absolute zero, which is 0 degree Kelvin, cannot be achieved in practice. So the cold reservoir temperature can never be zero. So because of these two limits, the efficiency can never reach 100%. Next topic, let's talk about heat pumps or refrigerant devices. A refrigerator, air conditioner and heat pump all work on the same basic thermodynamic principle. They are all reversed heat engine devices. The difference is mainly in what useful effect we want. For refrigerator, it removes heat from a cold space. And air conditioner, it removes heat from an indoor room and rejects it outside. And heat pump delivers heat to a warm indoor space or used for winter. They remove heat from a low temperature region and deliver it to a high temperature region by using external work input. Since this is against the natural direction of heat flow, the system needs external work input. If we see here, in this system, we have the cold reservoir. This is the low temperature region from where heat is removed. In case of refrigerator, it is inside the fridge. And in case of air conditioner, the air inside a room being cooler by an air conditioner. Or in case of heat pump, it is outside air. The heat absorbed by evaporator from this cold region is Q2. And the compressor supplies work input, which is W. And condenser rejects heat Q1 to the hot reservoir. Now if you look at the energy flow, the machine receives two inputs. It receives heat Q2 from the cold reservoir and it receives work input W. And the output from the machine is heat Q1, which is delivered to the hot reservoir. So according to the first law of thermodynamics, the energy balance should be Q1 equals Q2 plus W. This means the heat delivered to the hot side is equal to the heat taken from the cold side plus the work supplied. So because work is added in the system, So the heat rejected to the hot reservoir is always greater than the heat absorbed from the cold reservoir. For heat pumps and refrigerant devices, instead of thermal efficiency, we measure the performance, and we call this term as coefficient of performance, COP. In case of refrigerators and air conditioners, the main purpose is to remove the heat from the cold space. So the useful effect is cooling. So COP equals Q2 divided by W. Q2 divided by W. Heat pump works in same principle, but purpose is different than refrigerator and air conditioners. The useful effect is not cooling. It is heating the room or water. So instead of focusing on Q2, we focus on Q1, which is the heat delivered to the room. So the COP for heat pump becomes Q1 divided by W. Let's understand it with a very powerful real world concept, reversible refrigeration system. How the same system can work as an air conditioner and also as a heat pump. In countries like the US, Canada or Europe, the same system is used for both cooling in summer and heating in winter. This is called a reverse cycle air conditioner. The system components remain the same: compressor, expansion valve, indoor coil and outdoor coil. The only change is a device which is called a reversing valve. In cooling mode, indoor coil acts as evaporator and outdoor coil acts as condenser. Heat Q2 is removed from the room and rejected outside, and the work done is W, and useful effect is cooling. So COP of cooling mode will be heat removed from cold space divided by work input, which is Q2 by W. In heating mode, the refrigerant flow is reversed. Indoor coil becomes condenser and outdoor coil becomes evaporator. In this case, heat Q2 is taken from outside air, even in cold weather, and delivered inside the room. A very interesting question comes here. If the outside temperature is minus 5 degrees Celsius or even minus 10 degrees Celsius, how is it possible for a heat pump to still extract heat from such cold air and supply it inside the room? At first, this sounds confusing because we normally think cold means no heat. But that's not true. Let me explain this very clearly. Temperature is actually a measure of molecular motion. Even at minus 10 degrees Celsius, air molecules are still moving. That means they still contain thermal energy. Only at absolute zero, which is minus 273 degrees Celsius or 0 degree Kelvin, molecular motion completely stops. So as long as the temperature is above absolute zero, there is always some heat energy present. So now the question is, how does the system extract this heat? The answer lies in the refrigerant. The refrigerant used in heat pumps has a very low boiling temperature, much lower than the outside air temperature. For example, if the outside air is at minus 10 degrees Celsius, the refrigerant inside the evaporator may be at minus 20 degrees Celsius. Heat always flows from higher temperature to lower temperature. So even though the air feels cold to us, it is still warmer than the refrigerant. Therefore, heat flows from the outside air into the refrigerant. As this heat is absorbed, the refrigerant starts evaporating and becomes a low pressure vapor. Now comes the most important component, the compressor. The compressor does not create heat directly, but it adds energy in the form of work. It compresses the refrigerant gas, which increases its pressure and also increases its temperature. Now, the refrigerant becomes a high temperature gas, much hotter than the indoor room. For example, it can reach 40 to 60 degrees Celsius. And now this hot refrigerant flows through the indoor coil, which acts as condenser. So since the refrigerant is hotter than the room air, heat flows into the room. And this is how the room gets heated. So the useful effect in case of heat pump is not cooling, it is heating. So instead of focusing on Q2, we focus on Q1. What is the heat delivered to the room? So COP of heat pump will be Q1 divided by W. Now, if we see here, from energy balance, Q1 is equal to Q2 plus W. If we divide both sides by W, so we get Q1 by W is equal to Q2 by W plus 1. And Q1 by W is COP of heat pump. And Q2 by W is COP of air conditioner. So the equation becomes COP of heat pump is equal to COP of air conditioner plus 1. This means for the same machine, the heat pump COP is always 1 more than the air conditioner COP. This is why, because in a heat pump, the useful effect is the total heat delivered to the room. And this heat is not just coming from one source. It has two contributions. First, the heat extracted from outside air, which is Q2, and second, the work done by the compressor W. So the total heat delivered is Q1 is equal to Q2 plus W. So in heating mode, even the work supplied to the compressor becomes useful heat. So in this equation, COP of heat pump is equal to COP of air conditioner plus 1. This extra plus 1 represents the contribution of the compressor work. If we talk about practical application, instead of normal heaters or blowers, heat pumps are highly energy efficient. And these are used for heating large spaces like homes, offices, shopping malls, and industrial buildings. A conventional electric heater or blower works on resistance heating. It converts electrical energy directly into heat. So if you supply 1 kilowatt of electricity, you will get only 1 kilowatt of heat. So that means the COP of a heater is equal to 1. Now if we look at the heat pump, it doesn't create heat directly. Instead, it extracts heat from the outside environment and transfers it inside. And with the help of the compressor, it adds some work to increase the temperature. So for the same 1 kilowatt of electrical input, a heat pump can deliver 3, 4 or even 5 kilowatts of heat. So that means the COP can be 3, 4 or even higher. Now imagine heating a large building. If you use electric heaters, you will need a huge amount of electricity to maintain indoor comfort. This will result in very high energy consumption and very high electricity bills. But if you use heat pumps, you are taking advantage of free heat, which is available in the outside air. That's why heat pumps are much more efficient than heaters or blowers. So today, we understood the key difference between heat engines and heat pumps. A heat engine converts heat into work, while a heat pump uses work to move heat. If you found this helpful, don't forget to like, share and subscribe to Projexcellence Prodigy. Namaste, goodbye, Sampai Jumpa.